Hello and welcome to Nunley Math. I'm your host, Aaron Nunley. Thank you for joining us here today as we continue our discussion about how to solve application problems in algebra. Now, today is a little bit different of a lesson for us in that we're going to be talking about proportions, which is something that my students should already be very, very good at. I do like to go back and re-mention them in case there's some students that come from different backgrounds that aren't as familiar with those as they should be. And they are an important part of the algebra problem solving process. I know a lot of students that come to me learn how to work with proportions using a little bit of arithmetic and some logic, but they aren't really very good at about solving proportions using algebraic logic. Additionally, I find that a lot of students are who are even capable of working with proportions who struggle with proportions when they arrive in a word problem format. So just like we've talked about solving word problems that are literal translations, we're going to look at proportions as well. We're going to create some systems that will help us as we're solving these, some things that will keep us from making mistakes. But please don't think that this lesson is an entire study of proportions. Certainly there's a lot that goes into proportions we're not going to talk about today. If proportions are brand new to you after you watch this video, you may want to go back and watch a fuller explanation of this because I'm operating under some assumptions here regarding familiarity already. So let's walk through some terminology real quick and then we'll get to the meat of what we want to do, which is how we can solve application problems using proportions. When we talk about ratios, a ratio is a comparison between two different things. So for example, if I said to you the ratio of chickens to pigs, like this, we could set up a ratio that allows us to compare the number of chickens to the number of pigs using division. And hopefully most of you are aware that the ratio of chickens to pigs is 3 to 2. Now there are a lot of ways to write ratios involving the word TO, 2, 3 to 2, 3 colon 2. I've chosen to write these as fractions and we're going to do these exclusively as fractions today. It is also important to remember that we had to put the 3 first because we're asked about the ratio of chickens to pigs. The order of the numbers in our division reminds us of the order in the ratio. If I had put 2 to 3 or switched the order here, that would have said there were 2 chickens compared to 3 pigs, which would not be accurate. Consider the ratio of chickens to pigs now. Notice that we now have 6 chickens to every 4 pigs. The ratio or comparison between those is 6 to 4. And of course now we have a ratio of 9 to 6. Notice that every one of these ratios can be simplified just like you'd simplify a fraction. 3 halves, 6 fourths, and 9/6. All of these are different fractions that can simplify to 3 halves because they all express the exact same relationship. Even though the number of chickens and the number of pigs are both increasing, they're increasing the same way every time. Every time I add 3 chickens, I add 2 more pigs. 3 more chickens, 2 more pigs. 3 more chickens, 2 more pigs. And we can assume that pattern continues indefinitely. If I have 12 chickens, I'll have 8 pigs. If I have 15 chickens, then I would have 10 pigs, and so on and so forth. When you have two ratios that express the same relationship, we say that the ratios are proportional, or we shorten that to just saying that they are proportions. Now, this next slide has 2 sets of ratios. Chickens to pigs over here on the left is 3 to 2, 6 to 4, 9 to 6, and 12 to 8. It's the same relationship we saw on the previous page. Over here on the right-hand side, I have 2 to 3, 3 to 4, 4 to 5, 5 to 6. I have a different relationship between chickens and pigs. In order for these to be proportional, these ratios all have to express the exact same relationship. And there are lots of ways for us to test whether or not this is proportional. The one on the left is proportional. The one on the right, I'll go ahead and tell you, is not proportional. And as I mentioned, there are several ways I can tell this. I can take each of these ratios and write them in simplest form, just like I would a fraction. 3/2 is already in simplest form. 6/4 is 3/2. 9/6 in simplest form is 3/2. And 12/8 in simplest form is 3/2. If ratios are proportional, or if we're looking at a proportional relationship, when we put our fractions or our ratios in simplest form, they will all be the same. Notice over here on the right, this non-proportional example, 2/3 is already in simplest form, 3/4 is already in simplest form, 4/5 is in simplest form, and 5/6 is already in simplest form, but none of them has the same value as the others. That's method number one. Method number two, we could convert all of these into decimals. 3/2 over on the left, this 3/2 right here, is 1.5. 6/4 is 1.5. 9/6 is 1.5, and 12/8 is 1.5. When we put them in decimal form, they all must match, just like when they were fractions in simplest form, they would match. Over here on the right, 2/3 as a decimal is 0.6 repeating. But when I take 3/4 and convert it into a decimal, it's 0.75. Those do not match. 4/5 is 0.8. 5/6 is 0.83 repeating. Notice only the 3 is repeating. None of these match. In order for this to be proportional or a proportional pattern, they must all match. A third method we can use is looking for something called a constant of proportionality. Notice that if I take the top number of 3/2 and I multiply it by the fraction 2/3, it gives me the bottom number, which is 2. If I take the top number 6 and I multiply it by 2/3, I end up with a 4, the bottom number. In fact, every ratio here, if I take the top number and multiply it by that constant of proportionality, the 2/3, it's going to give me the bottom number. 12 times 2/3 is 8. If I try to do the same thing over here on the right, I take this 2 and I want to turn it into a 3, well, here I'm multiplying it by 3/2. 2 times 3/2 is 3. The top times 3/2 gives me the bottom. But if I take the second fraction, 3, and multiply it by that same constant, it does not equal 4. 3 times 3/2 is actually 4.5. If I take 4/5, take the top number times 3/2, it is not equal to 5. It's actually equal to 12/2, which is 6. And on the last one, 5 times 3/2 is not equal to 6. 5 times 3/2 is 15/2, which is 7.5. Notice 3 different ways that we can tell that these are proportional and that these are not. Now, there is one other way I want to talk about, and I saved it for last because it's really the focus of what we want to do here today. And that is this. I have the same proportional relationship here on the left. I have the same non-proportional relationship here on the right. And I'm going to use something called the means extremes property. The means extremes property says that the cross products of any two ratios in a proportional relationship will always be equal to one another. So what I can do is I can take any of these ratios here on the left, 3/2, 6/4, 9/6, and 12/8. And I can take any two of those, and I can find the cross products, or the means and the extremes, by multiplying diagonally. 3 times 4 and 6 times 2. 3 times 4 is 12. 6 times 2 is 12. Since those two cross products are the same, I know that this is a proportional relationship. Now, I said this must work for any pair, so maybe I tried 6/4 and 9/6, the second two. Multiply diagonally, multiply diagonally. Notice that 6 times 6 is 36. Notice that 4 times 9 is also 36. Or maybe you want to take the 9/6 and the 12/8. Cross multiply. 9 times 8 makes 72. 6 times 12 makes 72. And then I can just start mixing and matching. I went in order for those first few. How about if I take the 3 halves and the 12 eighths? Or so the 3 halves and the 9 sixths. 3 times 6, 2 times 9, both are 18. And just to be thorough, 3 halves and 12 eighths, cross multiply, you get 24 and 24. In a proportional relationship, anytime you do cross products, your solutions should be the same. Over here on the right, if I take the first two cross products, I get 8 and 9. They don't match. 3/4 and 4/5, 15 and 16. They don't match. 4/5 and 5/6, 24, 25. They don't match. 2/3 and 4/5, I get 10 and 12. They don't match. And lastly, 2/3 and 5/6, I get 12 and 15. They don't match. The cross products are a great way to quickly and efficiently check to see whether or not something is proportional. But the value of the means extremes property goes way, way beyond that. We do have other less efficient ways to tell whether they're proportional or not. But if we know that a relationship is proportional, then we can use the means extremes property to find missing values. Say, for example, the amount of money someone earns is being compared to how many hours they work. Money compared to hours. Most people earn the same amount of money every hour. So if you earn $3 an hour, you would earn $3 the first hour, $3 the second hour, $3 the third hour. So if we assume this is a proportional relationship, what we know is that if they earn $45 in 5 hours, we can predict how much money they would earn in 8 hours. And we would do it the exact same way we've been doing this, through cross products. 5 times x is 5x. 45 times 8 is 45 times 8. If these are proportional, the means extremes property says those two expressions should be equal to one another. Now, if you followed our solving equations series, you would know that the first thing we want to do here is multiply the 45 times 8. And then to get rid of the times 5, we're going to multiply both sides by the reciprocal or divide both sides by 5. Either way, we end up with x being equal to 72. This person would earn $72 in 8 hours. Now, I did the computation fairly quickly, hoping that that's already something you're fairly secure and comfortable with. If you struggle with the computation, you might want to go back and watch that a little slower, or go back and review a lesson on that. That's not our focus here today. Let's try another one. This proportional relationship compares the number of miles someone travels to how many minutes they travel. So maybe this is a runner, and this runner ran 2 miles in 17 minutes. 2 miles in 17 minutes. Now, if we assume this person can maintain that speed indefinitely, which is a huge assumption, we can predict how many minutes it would take them to run 5 miles. Notice miles is always on top, minutes is always on bottom. I can use my means extremes property. 17 times 5, 2 times x, the means extremes property says those two things should be equal to each other. Little computation, clear out my times 2, I'm left with 42.5. It takes 42.5 minutes to travel 5 miles for this person. Let's do one more. This is revolutions per second. Revolutions per second. A lot of industrial machinery has parts that spin in a circle. Those are called revolutions, and a lot of them move very, very quickly. So let's say this particular piece of machinery rotates 325 revolutions in 10 seconds. Now, being a machine, as long as it's on, we would assume that it would probably maintain the same speed, the same revolutions per second, so that we can predict how many revolutions it would take in 82 seconds. Notice revolutions are always on top, seconds are always on bottom. If I cross multiply, one side is 10x, the other side is 325 times 82. The means extremes property says those should be equal. Just do a little multiplication there. To get rid of times 10, I'm going to multiply both sides by the reciprocal or the multiplicative inverse. Some of you may have chosen to divide by 10. Either way, when you do that, x equals, should be 2,665. I got me a little typo there. So let's fix that real quick. 2,600, let's see, pen, let's scratch it. 2,665. Get rid of that. Get rid of that little decimal or that little comma there. Much, much better. Now, one thing I do want to point out is that it is typical or common or normal for people to put seconds on the bottom, minutes on the bottom, hours on the bottom. As a general rule, we like to have time on the bottom. That does not mean time has to be on the bottom in order for the means extremes property to work. What you'll find is that if you were to flip this entire thing over and do hours on top, money on bottom, 5 on top, 45 on bottom, 8 on top, x on the bottom, when you cross multiply, you would actually end up with the exact same expression or relationship. So it's not terribly important for what we're doing to have these in the order we have them. What is important is consistency. If hours is on top, hours has to stay on top or bottom. If hours is on bottom, hours stays on bottom. If money's on top, money stays on top. If miles is on top, miles stays on top all the way across. I mentioned that because now we're going to get into the meat of what we really need to talk about today, and that is how do we set these problems up using problem solving. So here's a problem for you. 4 out of 5 dentists recommend chewing sugarless gum after meals in order to fight cavities. Now, as soon as I see this 4 out of 5, my brain instantly thinks, oh, wow, that's a ratio. This problem can probably be solved using a proportion. If there are 631 dentists, about how many would you expect to recommend chewing sugarless gum? If there are 631 dentists, about how many would you expect to recommend chewing sugarless gum? Notice we are given a ratio. You're given a ratio. And then you are given an additional piece of information. This is typically how a proportion problem will work. They give you a ratio and then they ask you to find a missing piece on the other side of that ratio or to apply that ratio to a different set of values. Here is my personal recommendation, and this is actually a requirement for my students. I always have them start with a unit given find diagram. Notice that I have my bars lined up for 3 ratios, one here, and one here, and I've labeled what I expect to see in those 3 ratios. This first ratio is my unit ratio. That's where I'm going to decide what it is I'm talking about. In this case, the problem says 4 out of 5 dentists recommend chewing sugarless gum. So I know at least one of those things is who recommends chewing sugarless gum. The other thing I realize is since it used the expression out of, I know that this is a recommendation out of a total number of dentists. Now, most teachers do not require you to write this ratio. However, I find it very helpful because when I get over here, I'm going to have to make sure that the number that recommends stays on top and the total number of dentists stays on bottom. The hardest part for students at any grade level in setting up a proportion for a word problem is making sure the numbers go in the right place. Once the numbers are in the right place, almost everybody solves these correctly. The most difficult thing is getting them in the right place. This is the best way to make sure that happens, is by having this unit ratio written. Notice they told me 4 out of 5. So I know I've been given 4 people recommend out of a total of 5 people. Once they give me my ratio, which they always will, I will be asked to find something. Either they will tell me how many recommend, and they will ask me what the total is, or they will tell me the total and ask me how many recommend. Which piece of information did they give us? If there are 631 dentists, about how many would you expect to recommend? Notice the question is, how many would recommend? They want us to find how many recommend. That's what they're asking us to find. So I plug in my values. They told me the total. They asked me how many recommend. I've got the proportion set up and I'm good to go. I'm going to use that means extremes property, 5 times x, just like I did on the other slides, 4 times 631. Those have to be equal to each other. The hardest part of the problem is done. It's just multiplication, get rid of the times 5, you have your solution. Since it's a word problem, my students would be required to write this out. About 505 of the dentists recommend chewing sugarless gum. It's always appropriate when you're solving word problems or applications to give the answer in a sentence. Let's do one more of these. I would recommend that you try this on your own before watching the video. I'm going to keep right on going. When you do this on your own, try using that tool, unit, given, and find. That should help you quite a bit. The wait time to ride a roller coaster is 20 minutes when 160 people are in line. Notice we're comparing the amount of time to the number of people. At this rate, how long? They are asking me to figure out the time when there are 220 people. Notice I filled in my unit. I know the wait time goes on top and the people go on bottom. It's 20 minutes when 160 people are in line. I know they asked me to figure out how long, so my variable is the wait time. And they give me the number of people. There's 220 people. What's the wait time? You just finished the hardest part of the problem. Cross multiply, those have to equal. Multiply your numbers together, get rid of your times 160, your answer is 27.5. The wait time is about 27.5 minutes when 220 people are in line. Now, a couple things for you. Notice in this particular example, I had time on top. As I mentioned, as long as you're consistent and time stays on top, it really is not going to make a difference where you put that. Just be extremely, extremely conscientious. Make sure you put the units every time. I know you're going to want to skip that because my students try and skip it all the time, and guess what happens? They get the numbers in the wrong places. Take the time to do it right. It's always better to do it right than to end up having to do it twice. As always, thank you so much for watching. I hope this has been helpful to you. If you enjoyed this or if it provided some value for you, please make sure you leave me a comment in the comment section so that I know you're watching. Also, take the time to like and subscribe and turn on your notifications so that as we're working our way through Algebra 1, you can follow along with us. Let me leave you with a word of inspiration from the Rock, Dwayne Johnson himself. There is no substitute for hard work. Always be humble and hungry. Dwayne "The Rock" Johnson. Thank you, Rock, for not suing me for putting this on my video. As always, thank you so much for your attention.